In order to talk about exact equations, we need some background, in particular partial derivatives. A partial derivative is a derivative holding all but one variable constant. And here we're actually talking about multivariable functions. Suppose we have a function f of xy is equal to x squared times y cubed. We're going to take derivatives of this, but since we have two independent variables, we need to denote which is the independent variable that we're taking a derivative with respect to. And there are two ways to write that down. One would be f with a little x at its foot, it's a subscript there, or we use a curly d derivative notation to denote this derivative of f is with respect to x, but this d is here to let you know there's another independent variable. And when I say holding all but one variable constant, that means x squared is our variable, y cubed is to be treated as a constant. So we're going to differentiate x using the power rule, and y cubed just comes along for the ride using the constant multiple rule. In the same way, we can find the partial of f with respect to y. The notation is the same, except we're indicating that y is the variable that we're differentiating with respect to. X squared is the constant now, and so differentiating y using the power rule, we get 3x squared y squared. Now I'm going to go to another step of differentiating, but I'm going to use the subscript notation exclusively now. If I start with what I had already differentiated partially with respect to x, so fx, and then decide to differentiate that result with respect to y, then my starting point here is 2xy cubed, and differentiating that with respect to y is going to give me 6xy squared. Looking at what we have over on the right, if I take what I had partially differentiated with respect to y and then differentiate it with respect to x, we're going to get 6xy squared. And notice that these two are equal to each other. It's not a coincidence. These are called mixed partial derivatives, and a theorem from multivariable calculus is that second mixed partial derivatives are equal, provided the derivatives are continuous. There are some conditions that we're not going to get into right now. Now we're going to step back into calculus a little bit and recall that if y is equal to f of x, then the differential of y dy is f prime of x dx. It's basically a rearrangement of the fact that f prime is dy dx. And this is called the differential of y. If we now consider z to be a function of x and y, then the differential of z dz, it's got a similar expression. Now let's go back up here to dy equals f prime of x dx. F prime of x is a slope for any value of x. Well, that's rise over run. The dx we can think of as run because it's a horizontal distance, and when we divide out the runs, we're left with rise, which is exactly what dy, the differential of y, is. In the case of the differential of z, we have rise over run when x changes, but we also have rise over run when y changes. So the differential of z is fx dx plus fy dy. We again have rise over run for fx, then times run for dx, and that would be the rise when x changes. And then again, rise over run is fy, dy would be run in the y direction, and ultimately the run divides out and we have rise when y changes. When both x and y change, we end up with dz, the differential of z. This is what's known as the full differential of z, or the exact differential. That word exact there is where these equations, exact equations, get their name. Okay, we're going to set that aside for the moment. Let's consider the multivariable function f of xy is equal to x squared plus y squared. For f of xy equals some value c, we have x squared plus y squared is equal to c. Now, to get an idea of what's happening here, remember f of x, y, maybe not remember, I will introduce to you that f of x, y is actually the z coordinate. And so here, when we say f of x, y is equal to c, we're actually fixing the z coordinate. And x squared plus y squared is a circle. Now, we can say it's a circle of radius square root of c, but I'm really not so interested in the fact that it's the square root of c. I'm interested in the fact that for a z value, we have a circle. Now I have here a 3D coordinate system, and I'm going to draw this paraboloid, which is actually what the graph of f of xy equals x squared plus y squared looks like. Don't worry, we're not really going to live in this topic for very long. But what I just said was that if we fix a value for z, then we have a circle of a specific radius. And so we can think about z increasing, and as we go up this paraboloid, we end up with a circle. Each of these circles is called a level curve of the surface f of xy, and that type of equation, x squared plus y squared equals c, or more generally, f of xy equals c, is actually going to be the solution that we're looking for when we look at exact equations. And now I'm almost ready to introduce them. For the level curve, f of xy equals c, the exact differential is the full differential on the left-hand side, fx dx plus fy dy, and the derivative of c on the right-hand side, since c is a constant, that derivative is 0. Now for our work, we have a slight relabeling. We're going to consider m dx plus n dy is equal to 0. The solution to which is f of xy equals c. In other words, we're looking for the function f of xy that belongs on the left-hand side of that level curve equation. Now it's useful to note that our author, instead of using fx, is using m, and instead of using fy, is using n. Now a few minutes ago, I said that second mixed partial derivatives are equal. So if I start with a function f, partially differentiate with respect to x, and then y. Start again with f, partially differentiate with respect to y and then x, I get the same result. If we have an equation that's an exact equation, then the function in the term that has dx is a partial derivative with respect to x, and the function in the term that has dy is a partial derivative of some function f with respect to y. In order to understand what's happening here, I find this diagram to be pretty useful. Starting with a function f of xy, if we partially differentiate with respect to x, then we get this function that our author is calling m. If instead we partially differentiate with respect to y, we get a function that we're calling n. If I then take those functions and partially differentiate m with respect to y and n with respect to x, I've now created mixed partial derivatives. Because remember, m was a partial with respect to x already, and n was a partial with respect to y already. And so these two should be equal. Now we're going to be starting with an equation that is m dx plus n dy equals 0, or an equivalent form. And the first thing we got to do is find out, is this actually exact? So m and n are our starting point. We find partial derivatives to see if the original equation was actually exact, right? So this is a test for exactness. If we find that these results are the same, these partial derivatives, then we know that m and n came from the same function f, and then we can find f, and our first step would be to maybe take m and partially integrate it with respect to x. You can kind of see how that works, I hope. And that's what we're going to see in our examples.